All right, good afternoon, everyone. I'm excited because I'm here today and I get to talk about one of my my all-time favorite topic. My name is Aditya and I work on the observability team at Stripe, primarily on our open source monitoring tools, and you'll see one of those in a moment. At Stripe, we provide a simple, unified API that enables businesses of all sizes to accept payments online. And last year at Monitorama, you heard from one of my colleagues, Corey Watson, on how we built a culture of observability at Stripe. Today, I'm going to tell you about how we've built and are continuing to build the infrastructure of observability at Stripe. So you've been told that this talk is about tracing, and it is. But when I say tracing, it might not just be the kind of tracing you're thinking of. When I talk about tracing, I mean full cross-sectional visibility into all aspects of your production systems, complete with context and continuations of state, whether or not that's tied to an HTTP request response lifecycle. And if you're a big company like Google or Twitter, you can create your own integrated tool that handles all of that for you. And Google has done that. But for the rest of us, we're probably relying on open source or third-party vendors for at least some portion of our monitoring stack. And it's hard to get fully integrated cross-sectional visibility into your code if you're using multiple tools because there are always going to be gaps in between them. But fortunately, there's a way that companies smaller than Google can get this same level of visibility without writing their whole stack from scratch in-house. And the secret there is all in the metrics pipeline. So I'm here today with one goal, to inspire you all to take ownership of your metrics pipeline. And not just any kind of metrics pipeline, but an intelligent and context-aware pipeline that can help you achieve the pinnacle of system observability. So some of the stuff that I'm going to talk about today already exists in our open source tool called Veneur. Veneur is our take on an intelligent metrics pipeline. But some of it, that's what we'd like Veneur to become. And that's the exciting part. That's what you can help us out with. We want to make intelligent metrics pipelines like Veneur the gold standard of monitoring in our industry and make that accessible to companies of all sizes. We built the first version of Veneur ourselves at Stripe, but we're not the only ones using it or even contributing to it. Sentry and Bluecore are two other companies that have monitoring and runtime data right at the core of their products, and they both rely on Veneur for their metric pipelines. So let's start with the story. It's 3:07 in the morning, you're in bed, you're asleep and dreaming, and suddenly your pager goes off. Now I know this has never happened to you, but let's just imagine. So you're a little bit annoyed that you want to get back to sleep as soon as possible, but you need to figure out if there's a problem. What's the first thing that you do to diagnose it? Well, you probably pull up a dashboard. And here you can see, all right, the API success rate has dropped just below a threshold. You might be able to see the red dotted line. OK, so some requests are failing. But why are they failing? Now, for all we know, someone's written just a bad web crawler and it's generating a ton of 404s. Like, no one really needs to get paged for that, right? So how do we test that hypothesis? Well, we look at another dashboard. And on this one, we see, OK, there are some 404s, but there are also some sporadic 500s. So some requests are clearly actually failing in a way that's problematic for us, in a way that we do need to address. But why? We don't have any more information about those requests here on this dashboard. So we look at another dashboard. And here you can see, OK, we've got hundreds of boxes that are involved in these requests. And of those, only 4 are actually causing problems. And in fact, not for all requests. Notice that these are orange. They're not bright red. So that means that it's only some requests that are failing. But why? What is it about those requests? Is it the users? Is it the country that they're from? Is it the HTTP methods that they're using? We can't keep track of all of those factors because the cardinality of the data is too high. There are too many axes to keep track of, both at an implementation level and also to present in this dashboard. So there's no context here, and that's a problem. We want to de-anonymize our dashboard data. So to de-anonymize it, we might look at another tool, another dashboard, which are our logs. The problem with logs is that even when given access to structured logging, most people use them as literal log line, just text that logs just a pure chronological log. And it's possible to extract that information into something like, say, a histogram, but even with the absolute best of search tools, that's a lot more thought than you really want to have to put into it at 3 in the morning. Remember, you want to get back to bed as soon as possible. And oftentimes, you're just going to be poking at individual log lines anyway. Because how many of you have written log lines that look like this? Yeah, I see a few people raising their hands, and I think, and I heard some more laughter, so I'm assuming there are even more than that. Like, I'm making it look a little silly here, but when you think about it, most uses of logs follow this overall pattern. You don't actually even care about you don't even actually care about the text of this string right here. You know, about to query object, that doesn't mean anything. It's just the name of the log, and it's a way of disambiguating that line from other log lines to confirm that, yes, that particular line of code was run on that particular object ID. So when you think about it in this light, you realize you're just using logs like a runtime debugger. It's GDB, but by human. And so reading through the logs to find a bug, that's really just one step away from actually pulling up your source code, not looking at your tools at all, and just running through that, loading that into your head, and trying to analyze it. Well, why might my code be failing right now, in theory? I would go so far as to say, and in fact, I have said this, I've written about it, you can check out my feed if you're curious, that you should never have to look at logs. If you have to look at logs, something is wrong. It means that there is a gap in your system's observability tools. And one other tool for filling in that gap is request tracing. So, okay, fine, we go to another tool now. So if you're lucky, yes, you've got request tracing implemented around the part of the code that's breaking. But you might not. Like, you might have tracing implemented at a function level, and in this case, you really need visibility into a certain block because you know that that hot loop is causing problems. And even if you do, it's not wholly integrated with the dashboards that you were just looking at. You know, you have to go to another tool, you have to come up with another query that matches that corresponds to the data that you were just looking at. And so now you've looked at 5 dashboards on 3 separate tools just to evaluate the problem. It's 3:30 in the morning. You still don't even know what's going on. And at this point, for all you know, you could be up all night. So in physics, all matter is built off of certain fundamental particles. We have protons, we have electrons, we have neutrons. And all matter in existence, everything that we can see, is built using these fundamental particles. And in monitoring work, everything we see is also built from certain fundamental particles. We have metrics, we have logs, and we have traces. The challenge with metrics is that there's no context, as we saw. And the problem with logs is that they're too granular, there's too much context, and they're hard to aggregate in a useful and meaningful way. And the problem with request traces is that they require planning to use effectively. And that's actually not something that's limited just to request traces. It's a problem that's shared with all monitoring and observability tools. Because monitoring information is only going to be useful if developers have put in the time and the effort to predict, and not just to predict, but to successfully predict which parts of the code are the most likely to break and what information would be needed to debug that code from a broken state. You can think of this like the problem that we have with tests. You know, it's relatively easy to write a test case for a bug that you've discovered. But it's a lot harder when you're writing the code the first time around to figure out all the potential edge cases and exactly what you need to write for full coverage in your tests. And metrics are like tests, but the stakes are even higher because by definition, you're almost only ever interested in your metrics when things are already going wrong and going wrong in production. So this is one of the main reasons why they always say that the people who write a service should be the ones who are on call for that service. It's not really a punitive statement like, you know, if you don't instrument your code, then you're going to suffer for it. No, it's just a practical observation that those are the people who have the context necessary to parse that information quickly at 3 in the morning, and they're also the ones who have the context to instrument their code at the time they're writing it. They can put themselves in their own shoes. So let's imagine for a minute, like, what do other engineering fields do? Like, what if we built houses this way? If we built houses the way that we built software, the builders would never be able to leave your house. They would have to stay there and operate every single door and window for you. If your light bulb went out in the middle of the night, you'd have to call them. They would have to run over and take a look and say, yeah, it looks like your light bulb has fused. I mean, we don't do this for any other kind of engineering, so we shouldn't do it for software engineering either. And this is what observability means. It means designing the interfaces to facilitate visibility into your systems for whomever is actually going to be operating them at runtime. So let's wind the clock back by 12 hours. It's not 3:07 in the morning now, it's 3:07 p.m. the day before. And we're not the developer who just got paged, now we're the developer who wrote the code that caused the page. And it's okay, we're not here to point fingers. Like, raise your hand if you've ever written code that caused someone else to get paged. Okay, yeah. That's like 80% of the people are raising their hands. The other 20% are total liars. So in this case, we're writing a really basic web app. We just need to fetch and return objects from a database. There's no ACL, no transformation, nothing fancy going on. But it's an important endpoint, so we need to monitor it. We want logs, and we want metrics, and we want traces. Like, let's say our database client is tracing aware. How might we instrument this code to get all of that? If you want all three, you'll end up with something like this. So first, we set up a trace for the stuff. Then we actually do the database call. Then we report the thing that we did, and we track the status. Then we log the thing that we did, or the thing that caused us to do the thing we did, and we log the query parameters. And then we set the state on the trace. Who wants to write code that looks like this? Yeah, not a single hand. I really hope not. This is incredibly boring. Do you know how boring this was to write? This is so boring that I almost didn't even finish putting together this slide for the talk. It's so boring that, in fact, I was looking through it and I noticed there's actually a typo. The object, it doesn't get assigned anywhere. But I just couldn't be bothered to go back and fix it a second time around. I was like, no, it's all right. This is just an example. That's how boring this is. And it's for a slide demonstrating how tedious this is. So there's no way that we can expect developers to go through this whole song and dance every single place in their code anytime they do absolutely anything that might break, which means absolutely anything, just in the vague hopes that that data might be useful at 3 in the morning. So at most, what we can hope is that developers remember to write one line to instrument their code for observability. And even that's not enough, because if they have to sit and think about which one is going to be useful, then we failed them. We can't have them thinking, well, all right, this request, I need to emit a metric, because I need to monitor this, and I need to know the success. So, okay, I'll tag that. And, oh, it could be helpful to know the country, so we'll put that there. And also the IP address. So, oh, wait, nope, the cardinality, that's going to be too high, so I guess we'll just have to put a log. No, if they've gone through that whole process, they've long forgotten about it. They're not instrumenting it at all. And that's because we have failed to design a system that's architected for observability. So let's think, why is it that these three are separate libraries in the first place? Well, they're separate libraries because the data is actually going to 3 different places. And it's going to 3 different places because the storage and the query infrastructure is radically different for each of them. And it's different because of performance. Because the performance requirements for efficiently emitting, storing, and then querying those types of data are completely different. You know, StatsD or Graphite, it's not capable of handling the kind of load that we need to send it if we wanted to give it, our log volume. But Elasticsearch, it's not set up to index data the way that we need in order to get request level traces out of it. And even if you're using a product that combines 2 or more of these in a single interface, like the way Grafana will allow you to see both metrics and tracing products, they still have different backends that are powering all of this. But we're engineers. We know that implementation details should never dictate the interface that we use to interact with something. If we do, then that's a recipe for bad usability, which we just saw a couple slides ago. So let's look at the high level. I mean, there are 3 particles of data that we're sending. We're sending logs and metrics and traces. But if you squint, they're really not all that different, are they? Like, we could literally emit all of our log lines as statsd metrics just using the log text as the metric name. And when we structure our logs, we're just creating key value pairs. And that's essentially what metric tags are in the first place. So if we didn't have to worry about the performance requirements of it, the load, the data itself is actually shaped the same way. And traces are also pretty similar to metrics as well. The difference in traces is how we expect to be able to aggregate them. With traces, we're adding a few special fields as our tags. We're adding the span ID, the trace ID, the parent ID, and we want to be able to do an inner join on individual spans, individual metrics that we're emitting. And that's not something that statsd is capable of. Like statsd, it treats metrics anonymously. It does the aggregation in bulk. But again, the data itself is pretty much shaped that way. The difference is just how we handle it downstream, how we're aggregating it, or how we're interacting with it at a performance level. So what if we then just had a single interface for emitting all of these types of data, and we could then decide later on how we wanted to handle and represent them? So this here is my I want a pony slide. And I was so happy, by the way, because when I looked for images of ponies online that were freely available, the first thing I saw had 3 ponies on it. And it's perfect, Because I don't just want one pony. I want three. I want metrics, I want traces, and I want logs. I want all three of these. Well, it turns out we can do this. Because at Stripe, we're in the business of making simple, unified APIs across legacy systems. And we're in control of our data ingress. So we can have an intelligent pipeline that operates on that full fire hose of data. So from our service, we just have to then emit a single particle of data, and that particle contains the union of all the information necessary to construct a trace or a metric or a log line. And at Stripe, we've dubbed this the SSF, the standard sensor format. So then all we would have to do is make it easy and convenient for the developer to emit all of that information, that particle, with one short line. And then our pipeline determines how best to aggregate and synthesize that particle. So you might wonder, like, what might this look like? Well, this is just an example. It'll look different in different languages, but hypothetically, this is what we could do. You'll notice, I mean, I don't even remember how many lines we had in the previous slide to instrument it, but we've collapsed that all now into one single call, one single function, and it's a pretty easy one to write. We've combined the metric name and the log name because they serve basically the same purpose. And before, we tagged the success status on the metric, and we logged the query parameters, so we sent them to different places. But here, we're putting all of that in the same piece of information, and we know that our pipeline is going to figure out how to split that up and handle it downstream. So Veneur will take a stream of these SSF particles, and it decides not just where to route the particles, but actually what to make out of them and how to do it. Each particle here contains the full amount of information, but each icon represents what Veneur might use it to build. You might just barely be able to see that red line there. So like this one, Veneur, it sees that particle and it turns it into both a log and a metric. They both get emitted and sent downstream. And this one here, well, Veneur started doing the same thing as well, but creating both a log and a metric. But then it noticed that, nope, the cardinality on that is going to get too high. So it dropped the metric and it just sent the log, a log line downstream. And then here it sent a log and a trace instead. You can imagine, might send a trace and a metric or just a trace span. And then these three are kind of interesting. Well, Veneur is going to look at each of those, and it's going to create a log line and a metric for each of those individually. But then it also notices that they're actually shaped pretty similarly, and there's some more information that we can glean out of this. So it will actually extract that and pull that into a histogram, which is yet one other piece of data that also gets sent downstream to our tools from these particles. So the key thing here is that we're not going to send, our full log data to Datadog. Whoops. For example. But, let's see. Yeah, we're not going to send like our full log data to Datadog, but we know which SSF particles were used to build that histogram because we are the ones building it. We're doing that ourselves in the pipeline. So if we want, we can record that relationship, and that allows us to integrate our monitoring tools more effectively, however we want. And that's the crux of it. Veneur isn't a replacement for any of these tools. Veneur is a pipeline that lets you integrate and leverage your tools better together. Veneur uses the SSF particles to build the data that tools like Zipkin or Open Tracing, Grafana, Elasticsearch, and all those tools will then present in a usable form to developers who need to operate and run the code. So the developer who writes the code no longer has to decide at the time they're writing it how they think that they will want that information represented ultimately later on when they get paged. They just have to make the decision to instrument their code in the first place, and then the pipeline will do the heavy lifting for them. So let's see some examples of what it looks like and what we mean when you say that we can leverage these tools better. Well, when processing data, just in general, we always have a trade-off we have to think about between accuracy, precision, and performance. And we can't get rid of the need for that trade-off. It's always going to exist. But we can ensure that that trade-off will work in our favor at each step. You can think of it like going to Vegas. Like, the house isn't going to win on every single hand, every single spin of the wheel, but ultimately, the house is going to get what they need. And aggregation is a good example of this. So like, let's say we're analyzing API latency. We can't just send and store everything. Like, we're not going to send and store the latency associated with every single request because aside from the load that that would cause in our systems, it's not useful. As a developer, you can't look at at all of those pieces of data individually and make any reasonable decisions about it. So we use aggregates. We'll use something like the average or the median or the maximum. And those statistics will capture some of the qualities of the data, but it's lossy. If you know those exact statistics, you can't reconstruct the full data set, but you have an idea of the general shape. You have maybe what you need. Or another example, we might want to count the number of unique IP addresses that are logging in during a particular interval. So and we might not just want to do that during discrete and mutually exclusive intervals, but we might want to say like these 10 seconds and these 10 seconds and these 10 seconds, but then also this minute and also this entire hour. And if we want to be able to stack it like that, we don't want to use potentially unbounded memory to hold all of that. So even if we have a trade-off, though, the point of an intelligent pipeline is that we can stack the deck in our favor. We can make that trade-off at a point where we have the information available to us, and we can ensure that if we're ever going to, we have to drop some of that data, we can ensure that we're only ever dropping parts of the data that we don't need. So let's see an example of how that works in practice. Well, for starters, if our monitoring pipeline goes down, you're hosed. I mean, if your monitoring pipeline goes down, you can't see anything into your systems. So our pipeline needs to be highly available. And to do this, we use an architecture that's distributed, but also one that's tiered to manage the trade-offs there. So to start off with, we run Veneur on every single box in our fleet, and that gives us a nice property. It means that as long as the box itself is up and running, any services that are running on that host, they can report metrics, and those get sent directly downstream to our many. I drew one here, but there would ultimately be actually multiple downstream tools. But that gives us an aggregation problem, because if we want something like the maximum latency, that's easy. We can calculate the maximum on each box individually, and then look at all those maximums and take the maximum of that. But we can't do that with all aggregates. Not all aggregates work that way. For example, medians or any percentiles. We can't combine medians. They're not monoids. There's no mathematical operation that will take the median of 50 different subsets of the data and then give you the full global median afterwards. It's just not mathematically possible. So we'd have to keep all of the full data set and still send that to a single global aggregator box. And that defeats the whole point, because we've now introduced a single point of failure, and we've also reintroduced the load problem, where we're actually sending all of our metrics still to a single aggregator, even through these even through these multiple sources. To give you an example, like way back, we tried this with Graphite. This is before we even had Veneur. And we just sent heartbeat metrics from every box we had to a central Graphite instance. And we found that we could drop anywhere from 30 to 50% of those metrics on the floor, the heartbeats, just because the load was so high and Graphite couldn't handle that. So we need something that will actually properly horizontally scale. So instead of doing that, we use a ring buffer, and we consistently hash our metrics when we aggregate them. So let's say host 1, it emits red, blue, green, or red, blue, purple, and green metrics. It will always send the red metric to the first box, first aggregator box, the blue one to the second, and so on. But we consistently hash it. So all the other hosts will also send the red metrics always to that first box. And they don't need to communicate with each other and coordinate beforehand which box they're going to send it to. We use a consistent hashing scheme, and it happens for us automatically. And this gets us the best of both worlds, because now if any one of those aggregator boxes goes offline, well, that's fine. I mean, we'll lose one in n of our aggregates, but we won't lose all of them. The other boxes will still continue reporting aggregates and sending them downstream. And in fact, we'll only lose then the aggregated data, because remember, these hosts also have the ability to send non-aggregate data downstream to tools as well when appropriate. And so we'll still preserve those, and we don't lose it forever, because even if we don't immediately spin up a new box to replace it, well, these hosts, they now know that they only need to consistently hash across 3 hosts instead of 4, and they'll still use the same scheme to communicate, and they will still send all the data for each particular metric to the same place to be aggregated. So now, my background is actually as a statistician, so this is the part that I could easily talk about for like an hour. If you want the full picture, come find me at the breaks, and I'll tell you all about this in much more detail. But I just want to give you a taste of what it means when we say managing those trade-offs in a statistical sense. So I did say a moment ago that there is no mathematical operation that will let you combine, take medians of medians in a mathematically valid way. And that is true if you're dealing with exact operations. But we don't have to. We could use an approximation as long as we're confident that this probabilistic algorithm will have the properties that we need. And t-digests really fit the bill for us here. T-digests are a great way for us to recursively calculate probabilistic approximate percentiles in an online fashion. So we can calculate our percentiles in an approximated way on each host locally, and then send those approximations downstream, and we could then run the t-digest algorithm again on those percentiles, and it is actually mathematically valid. Again, it's an approximation, but as long as it has the properties we need, we're fine with that. And it turns out they do. Because the way that t-digests work is they trade off variance in the center of the distributions for precision at the tails. So in this case, the variance on the median of any metric is actually relatively large. It's not actually huge, but it's much larger. But on the 99th percentile or even the 99.9th percentile, it's tiny. In fact, by the time you get all the way out to the 99.9th percentile, you might be dealing with the exact value right there. And that's what we care about, because as long as the variance in the median is bounded by the stuff in the tails, those are the ones we care about. We care about the requests that are slow, that are problematic, the ones that we actually need to look at and piece apart individually. So it's not about getting rid of and eliminating these trade-offs entirely. It's about making those trade-offs work for us and making those decisions in a more dynamic and customizable way. So once the pipeline is intelligent, we now just need to build our interfaces to work with all of this. And what does that look like? Well, you can help us figure that out. We have some ideas, and we've started building some of it, but there's a whole lot left to be done, both with the pipeline and with the downstream tools. So now that we've defined the subatomic particles and we've contained them in the SSF, our grand unified monitoring particle, we can build the monitoring universe that we want to see. So let's go back to the story at the beginning. It's 3:07 in the morning, you just got paged. You're still not thrilled about being woken up, but that's okay. You know that your systems have an intelligent metrics pipeline, and that will do the heavy lifting for you. You pull up your dashboard. You notice that API requests have dipped below a threshold. Okay, fine. But you have context there. You could actually pick apart some of those individual requests in a way that is connected back to the corresponding trace spans or log lines, and you can see the individual status codes. You can see, yes, there are actually some requests that are giving us 500s, and you can look at the relevant pieces of data. It will pull apart for you a histogram. You can look at the latency. All right, the latency is fine. The latency is definitely not an issue, but you notice something else interesting, another part that it highlights, and that's the IP addresses. Now, it doesn't keep track of all the IP addresses for you. The IPv4 address space is way too high, but all we need is the /24 subnet, and that is actually a manageable space for our tools to handle. And there, we notice that all the failing requests come from the same 3 subnets. And then you realize that this traces back to a configuration change that was rolled out earlier in the day that only affects one certain data center. So all you have to do is flip the switch and you're good to go. So you got paged at 3:09. By 3:08, you figured out the problem, and by 3:09, it's fixed and you're back asleep, dreaming about this better monitoring universe. So in 2018, I want to come back to Monitorama and hear a whole slew of talks with people excited about the things that they are building using their intelligent metric pipelines, the things that this enables them to do, the ways that intelligent metric pipelines let them integrate tools together the way they couldn't before, or the way that intelligent metric pipelines let them record relationships between their monitoring data that previously they had no way of structuring, or the way that intelligent metric pipelines make it easier for developers to write and instrument observable systems in the first place. So let's do that. Let's make intelligent metric pipelines like Veneur the gold standard of monitoring, both at your company and across the industry, for companies of all sizes. Thank you.